Alright, so we've talked about congruent triangles and what can make triangles congruent, but today we're going to get into using those ideas in proofs. So we're using congruent triangle postulates, and we're going to start off with a reminder of congruent statements. So it says triangle QTS is congruent to triangle HVN, which angle is congruent to VNH, and which side is congruent to side QS. So that would be, change to white. So remember that the order of the letters tells us what is corresponding. So VNH is second, third, first in this triangle. So this one would be congruent to or corresponding to angle TSQ. So same positions, right? And V goes with T, N goes with S, H goes with Q. So angle TSQ. And then corresponding to QS, that's letter 1 and 3, would be HN. So this is going to be HN is congruent and corresponding to QS. All right, so we're going to talk about the five postulates we can use in proofs to talk about triangles being congruent. So if we're trying to prove that two triangles are congruent, these are the tools that we have. So these are tools to prove triangle congruence. We talked kind of about engineering, how that looks at this and with constraints. I also am making a separate video about how to look at this from a mathematical perspective. So a couple different ways to kind of understand these postulates, but since they're postulates, we don't really need proof for them. But if you want to kind of prove to yourself why they are the way they are and where they come from, there are two separate videos on that. So first one, side, side, side. So SSS, in a proof, you can write side, 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 or you can literally just put SSS as an argument, and I will take that. So for that to be used, though, we have to have shown that all three sides of a triangle are congruent to the other triangle. So you need to prove S, S, and S are true before you can use this to prove the triangles are congruent. Same thing with all of these. You need to prove each of the individual pieces in order to prove the whole thing. Second one, side, angle, side. So again, you can feel free to either write it out or abbreviate as SAS. And remember here what's important is this angle is the included angle between the two sides. So you'll know a side, and the angle between them. Here you'll know all three sides. So you'll have two triangles, and you have to show all three are congruent. Here we have side, angle, side, to where that's the included angle. Then we have angle, side, angle. ASA. So for that one, we have an angle, and then, so we have angle, angle, and then the side between them. So they're included side. Those three things are congruent, then we're good. And the last one, angle, angle, side, AAS. AAS we have in a triangle, we have this angle, and this side are congruent to this angle, and this side. So key thing here, kind of like, well, we haven't done that one. Key thing is the side is not the included side, it is one of the non-included sides. So the two angles are consecutive, and then the side is separate from those. Yeah, so the last one that I skipped over, SSA, because that one is kind of weird. So side, side, angle. Generally, you're not allowed to use this in proofs. So side, side, angle, if this angle, so if angle is acute, not valid. If it's obtuse, it is valid, but still generally it's not accepted as an argument in proofs. I don't know if we'll see proofs where that would be useful or not. I wouldn't worry about it for right now. But what you will see is a different version of this. So specifically for right triangles, you may see in the notes and in the proofs that we're doing that it's called HL. So HL is short for hypotenuse leg. So in hypotenuse leg, we have a right triangle specifically. So we know this angle is a right angle, and then we know one of the other angles, so that's our A. This is our, I guess that's a 90. Wait, I'm doing that wrong. Whoops, we don't know an angle. If we knew an angle, that would be fine. Okay, let's draw this triangle again. Okay, so we have a right triangle. We know these things. We know the hypotenuse, and we know one of the legs, and we know this 90-degree angle. So really, this is SSA because the angle is not included, right? Just like we said here. So in this SSA, you know side, side, not included angle, geez. Side, side, and not included angle. So SSA, not SAS, that one was valid. That's a good one. SSA is the one that's iffy. So here, this is a form of SSA because we have the hypotenuse and the leg and then this angle, which is not the included angle. However, since A is greater than or equal to 90, we can use SSA here, but they give it a different name. They call it hypotenuse leg, and they only make it valid for right triangles, which is kind of weird. So in most geometry notes, they only present it as being 90 degrees is the exception to SSA. But realistically, every triangle, if it's obtuse, and you know this angle and two sides, then that's valid as side-side angle, even though this is not the included angle. So I don't know why they don't have like obtuse angle side-side or something like that, because it would be valid. I guess naming it in the same order would be like side-side obtuse. That would be a valid thing, just like HL is. But you'll never see this in notes, and you'll probably always see that it says you're not allowed to use this, but realistically it does work as long as this is not acute. So HL is one you'll probably see showing up. I don't know what to tell you about it. It's just what it is. Okay, so our practice today and over the next few days is just proofs. So I'll do one or two of these proofs with you on the video, but the keys are on Canvas and they're pretty much just the same kind of proofs we've been doing. Just remember the goal in these is to establish the things that are in that postulate, and then we can use it to say the triangles are congruent. So here we have P. Let's actually go to maybe a slightly harder one. Let's go to number 3 for that one. We'll do one side, side, side. So it says AC is congruent to AD. So one big thing is I would mark that on the picture and put 1 dash there and 1 dash there. CB is congruent to BD. I would put 2 dashes there and 2 dashes there. And then it says to prove that ABC triangle is congruent to triangle ABD. So we look for, where is the third side of this triangle? Well, it's right here in this shared side AB. So in order to say that these are congruent by side, 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 so clearly that's what we're doing here. So our final argument is going to be SSS to say triangle ABC is congruent to triangle ABD. To lead up to that, we need AB and AB to be congruent, BC and BD to be congruent, and so on. So we have AC congruent to AD, that's given. Great. We have CB is congruent to BD, that's given. Great. To get our third set of sides congruent, we need to use the one thing that we said was never useful but actually has value here, because we literally need to say that AB is the same as AB. So segment AB is congruent to segment AB by the reflexive property. So reflexive property tells us AB is the same as AB. And again, formally, in order to use proofs for this, we need our statements to include all three pairs of corresponding sides, or all three corresponding sides as congruent. So we need AC to AD, CB to BD, and AB to AB. So yeah, kind of dumb, I know. Okay, so that's side, side, side. Let's look at a side angle side. We'll just go, I haven't really looked at any of these right now, but let's just go to number 7, because that includes some parallel lines. So these are going to bring in some more interesting things to the proofs, like bisects. So that's going to tell us two angles are equal. Midpoint, that's going to tell us that two sides are equal. And then parallel is going to let us use transversal rules. So these are more interesting because they involve angles. Sides are kind of boring. So we're trying to prove this, and we know we're going to end up using side, angle, side, which I'm just going to abbreviate. So we're going to use side, angle, side to prove that. I'm going to put that as SAS. So let's start off. HI and JG are given as congruent. I'm going to go mark that on the drawing. HI, JG. HI is parallel to GJ. I'm going to mark that on the drawing as well with my little arrows. So this is given. Next we have angle GJH is congruent to angle IHJ. So we need an argument or a reason that makes that true. So GJH is here, and IHJ is here. So when we have parallel lines and a transversal kind of thing going on, I like to extend those parallel lines a little bit so that I can see all of, and then my transversal that cuts across those two angles is here. So I'm going to extend it just a little bit as well. That way I can see my 8 angles. So these two are alternate interior angles, so that's what's going to justify this. So alternate interior. HJ is congruent to HJ. We just saw how when we have this shared side here, we can say that it is the same as itself by the reflexive property. And then to have side, angle, side, we have this side congruent, this angle, and this side. This angle is included between those, so that is side, angle, side, not the one we have to watch out for, side, side, angle. This one is good because it's side, angle, side. And since these are acute triangles, this one would be bad. Okay, so even though it's in the next section of notes, I'm going to skip down and look at a angle, side, angle problem. So we have this one. This one has a midpoint, so that's good. It brings in a new thing. So we have here angle BAC. BAC is congruent to angle DEC. That's here. So those two match. So I'm going to go ahead and write that down. Angle BAC is congruent to angle DEC. And it looks like they're doing one given per line to make these work out, so I'm going to go ahead and put that one all by itself. And then my other given information is C is midpoint of AE. So that means AC is congruent to CE because that splits them. So this was given. That's something I'm going to want to bring into my proof and say that AC, that segment, is congruent to CE. So that one comes from definition of midpoint. Next, let's see, we want to establish angle, side, angle. We have angle, side. That means we need this angle here to be congruent to this angle here. So that's BCA and ECD. So we need a way to say angle BCA is congruent to angle ECD. And to do that, we can see that these are vertical angles. So this can just be vertical angles. And then our last step would be what we're trying to prove is that triangle ABC is congruent to triangle EDC. And make sure that we recognize the order still matters, right? Angle A was our first congruent angle to angle E, so those are the first letters. And then if we go from A to B, that's not towards C, right? Because C is where our other shared angle is. So here we'd be going E to D. So A to B, E to D, and then we end up together at C is our third letter. So this is by angle, side, angle, where again that side is included between the two angles. Next we have one for AAS. So let's go here and let's see. Which one would be good? Bisects. We haven't done a bisects one yet, so let's do number 6. It says PR bisects QRS. So segment PR bisects angle QRS, and that would be given. And then we're going to mark that information on our drawing. What it tells us, since QRS was bisected, is that this angle and this angle are congruent. So we can go ahead and say that if we want to. That's what bisector gives us, is S angle SRP is congruent to angle QRP. And that would be by definition of angle bisector. Then we have our other piece of given information. Angle PSR is congruent to angle PQR. So let's mark that on the drawing. PSR is here. PQR is here. So now we have, this was given. We have two angles, and we're going to need a side to be shared. And remember, for two angles, it doesn't matter whether that side is included or not. We have angle, side, angle, if this side was equal. We also have angle, angle, side, if this one is equal, which it is. So we have PR is congruent to itself, PR, bireflexive. And then our finish will be AAS, will be our reasoning for the triangles being congruent. This should be the order they're named in, obviously, so we can kind of just copy that. But if it wasn't given and it said prove some triangles are congruent, we would check the order of things. So this one is named PSR. So it starts from the unlabeled angle, goes through the 2 mark into the 1 mark. So the other one, that would be PQR to follow that same pattern. So triangle PSR is congruent to triangle PQR. So hopefully after the proofs we've done, these will feel super easy and fast and not too challenging. There's extra practice on all of this stuff. I guess we should do one HL, even though it's a weird case. So HL, that's our case where SSA is usable and has a different name of HL. So here we have triangle LNP and triangle NNP are right triangles. So we know those are 90 degrees, and we also know they share that angle. So this is given. we have ML is congruent to MN. So ML congruent to MN, those are the hypotenuse. I guess we don't need to bring that information in specifically. This was given. I guess we don't need a step that's like definition of hypotenuse. I don't know. The next one, MP is congruent to MP. We keep seeing that. That's reflexive. And then this would be HL, or hypotenuse leg, as our argument for why they're congruent, because we know they're both right triangles. They have a congruent hypotenuse and a congruent shared leg. So that's how these proofs are working. Hopefully, like I said, they seem super easy. They're very basic. There's not a whole lot to them, so hopefully this is an easy part to this unit.